Good morning, everybody. Section 1.6, Day 2. And it starts with a warm-up here, and it talks about using the graphing calculator, but I'd actually like to use this to just talk through the process with everybody. So it says we're going to introduce stretches and shrinks. Well, that's, we know, not entirely true. And we also know that we should be using the more appropriate language here of compressions instead of shrinks. Remember, the vocabulary is important when you get to the AP testing. So introducing stretches and compressions. Set your viewing window. Let's not even worry about any of that. But what we would want to do is take a look at this and say, all right, if this is my parent right here, what's it going to do if I put a 1.5 in front of it? What will that accomplish for that graph? And here's what we know from past experience. We know that that 1.5 would be greater than 1, and so that would mean this would get a vertical stretch factor of 1.5. And we would absolutely see that in the graph. So if you wanted to graph that, feel free. Now on the next one, I see that there's a 2 that's in front of our square root function. And again, that's our a value when we think of y equals a square roots of x minus h plus k. And that a value is, again, greater than 1. So that would be a vertical stretch. But this one would be a factor of 2. Now I get down to the third one. And for the third one, I see it has a 0.5. And 0.5 as a fraction is 1/2. And we know that when we put a fraction between 0 and 1 in front of any of these, well, then we have a vertical compression. So this would be a vertical compression factor of 1/2. And so with the last one, pardon me, 0.25 is the same thing as 1/4 as a fraction. So this one is a vertical compression factor of 1/4. And just notice there I color coordinated those two top ones that were vertical stretches. Those are in blue. And then the two bottom ones are vertical compressions. And like I said, we already know that. We know that about A. So what are we supposed to get out of this box? Well, now we're going to talk about horizontal stretches and compressions. And all along, when I have talked about what happens with the x values, I have made sure to let you know that it's always the opposite of what we think should happen. So when we are underneath the square root and we see an x plus 2, we know that that actually goes 2 to the left. If we see an x minus 1, we know that that goes 1 to the right. It works the same way, no matter whether or not we're talking about as an h or a value that we have that's affected the x right in front of it. But it's the opposite, always. That's what stays constant with this. So now, as I look at my functions, I realize, well, look at what they did. They put that 1.5 in front of the x. Well, notice it's being multiplied. But because this is affecting the x, it's actually the reciprocal, thinking division, that we need to realize is happening for the horizontal changes. So if I have this 1.5 in front of the x, I think of that as a 3/2, and I realize, oh, well, what they really did was they divided this by 2/3. And that means this would actually be a horizontal compression factor of 2/3. So you have to think of it as we're multiplying by something that actually came from division by the reciprocal. So now when I look at the second one, that changes the way I look at that one as well, because I see that that 2 is connected with the x, and I think, okay, x's, everything's opposite. It looks like they're multiplying by 2, when in fact what they did was they divided by 1/2. And then for y sub 4, now I see that they've taken that 0.5 and multiplied that by x. So I think, okay, if that was 0.5, that's 1/2. That means they divided it by 2. So this is actually a horizontal stretch factor of 2. And the bottom one, 0.25, is the same thing as 1/4. That means they divided that by 4. So that would be a stretch factor of 4. So again, if we're constantly thinking, if something is attached to the x, x behaves in the opposite manner that we would normally think it would, then we can make our way through this. So this is our new piece of learning here. And from our objectives, we know that we were supposed to talk about all the transformations, including the horizontal stretches and compressions. So we have to say to ourselves, well, I know all the rest of them. Now I just have to think backwards about what's happening with those horizontal stretches and compressions. So let C be a positive real number, then the following transformations result in stretches or shrinks of the graph y equals f of x. Horizontal stretches or shrinks are y equals f of x over c. We have a stretch by a factor of c if c is greater than 1, and we have a shrink by a factor of c if c is less than 1. And this is exactly what I was just talking about. We're going to see what looks like multiplication, but in reality, it was division. And so if we see 2x, we have to think, oh, wait a second, that was actually dividing by a half. So that's going to be a vertical compression. And again, I'm looking up here and thinking, I wish they would have, used that language throughout here. So stretches are going to look like compressions, and compressions are going to look like stretches when we're talking about horizontal. So always think the opposite of what we think would happen logically is happening with the x. And then the vertical stretches or shrinks, we've learned those in the past. We know that if the number in front of the entire equation, whatever our parent function in there, is a number bigger than 1, then we're talking about a vertical stretch. And if we have a fraction that's between 0 and 1, then we're talking about a vertical shrink. Now, example 5 says, finding equations for stretches and shrinks, let C sub 1 be the curve defined by y sub 1 equals f of x equals x cubed minus 16x. Find equations for the following non-rigid transformations of C sub 1. So non-rigid means we're changing the shape, and we absolutely would if we had vertical or horizontal stretches or compressions. So this one wants C sub 2 to be a vertical stretch by a factor of 3. So what that would mean that we need to do is figure out where that would go, and of course that would go in the front, because that's our a value. So we would have to take 3 times x cubed minus 16x to make that happen. And we could certainly graph those, and we could see that where the blue is the original, that's our x cubed minus 16x. And then the black one is our 3x cubed minus 48x. So imagine that your function is made out of rubber bands, and you're holding the top and the bottom of it, and you have to stretch it 3 times as tall as it was before. And that's what we see in that graph. Now C sub 3 is different, because this one says C sub 3 is a horizontal, and again we'd want to say compression of C sub 1 by a factor of 1/2. So then that makes me realize that what they're really asking me to do is take my f of x function and divide that by 1/2. And like I talked about before, that's really going to look like it's been multiplied by 2. So it's really going to be f of 2x. So that means wherever we see an x in our function, we're going to have to change that to 2x. And that was, I lost the original way up there, that'll be 2x, the quantity, cubed minus 16 times 2x. Way back up here. All right, so now we do the math, and we get 8x cubed, because don't forget that that 2 has to be cubed as well, minus 32x. And again, when it says it's going to be a horizontal compression by a factor of 1/2, it's actually going to stretch the graph horizontally. So in this one, we see again that we have the original, and then we see that horizontal compression. So the blue one here is again our x cubed minus 16x. And now notice how if you were holding that to the right and the left and you squished it in, we would get the black graph. So when we have a horizontal compression factor of 1/2, our x's are actually going to be multiplied by 2. So thinking opposites. Things that work with the x are opposites. Example 6 says let's combine transformations and in order. Now there's a reason that we're doing this, and this is because order matters with transformations. So this says the graph of y equals x squared undergoes the following transformations in order. Find the equation of the graph that results. So the first thing we're supposed to do is a horizontal shift 2 units to the right. Well, we know from the past that means we have to attach that to the x because that's a right and left movement, but it looks the opposite of what we would normally think it should be. And then we need a vertical stretch by a factor of 3, and we also know that that is our a value, so that goes out in front. And then finally we have a vertical translation 5 units up, and that is our k value in the back. Now because this problem is about us seeing that order matters, we want to be able to compare these when we're done. So what we're going to do is we're actually going to write that one out in standard form. So that means we're going to come over here and we're going to write out x minus 2 times x minus 2 plus 5, or we're going to go ahead and remember the formula for a binomial squared. Most people just write it out twice and then do the FOIL. So x squared minus 4x plus 4 plus 5. Y equals 3x squared minus 12x plus 12 plus 5. So it will be y equals, I'm going to go over here, y equals 3x squared minus 12x plus 17 in standard form. And like I said, the reason that we're doing that in both forms, the first one is what we would normally think of when we're using our a, h, and k, and the second one is in standard form, so that in a minute when we do b here, we will be able to see that there is a difference. So with b it says now apply those transformations in the opposite order and see what happens. All right, so this time we're going to add the 5. Now, what that's done is it's taken our graph and it's moved it 5 units up, and that's what it was supposed to do. Now we have to do the vertical stretch by a factor of 3. So that means we're taking 3 times the entire graph, and I didn't want to scroll this up too fast here. Now we want that horizontal shift 2 units to the right. So inside here, we're going to need our 2 units to the right to make that happen. So now, I want to see how does that compare to what I had in the green. Well, I need to go ahead and put it in standard form, so it'll be 3 times the quantity x minus 2 squared times x minus 2 times x minus 2 for the x minus 2 squared, and then the plus 5. So we will get our x squared minus 4x plus 4 plus 5, and then 3 times x squared minus 4x plus 9, which is 3x squared minus 12x plus 27. So notice, we used the exact same transformations, but they were in a different order, and it did not end up with the exact same standard form equation. So this means order matters, and it absolutely does. And as I mentioned in yesterday's notes, there are many right ways to have the order and have it work, but there are also a lot of wrong ways. So one of the things I've done in the homework is I've shown you the older way of doing this, which would be by following the order of operations, but always making sure that vertical stretches, compressions, and reflections, horizontal stretches, compressions, and reflections are always done before the translations right and left, up and down. And that's because the order of operations tells us that multiplication always has to be done before addition and subtraction. So the easiest way for you to do these and learn them is from left to right. But as you look at the homework, you're going to see that I've changed the order so that you can see that yes, there are various ways to do this correctly, but there are also ways to do this wrong. Now, I don't put any wrong answers in the homework. But what I don't want is that you get to college and a professor tries to tell you, no, we're going to do it this way, and that you are arguing and saying, well, no, we're always going to do left to right. There are many correct ways to do this, and you need to know that. Just be careful that you are putting vertical stretches, compressions, and reflections before vertical translations, and that you are always putting horizontal stretches, compressions, and reflections before horizontal translations, right and left, and you'll be okay. Lots of right ways to do it, but there are some wrong. So example 7 says, let's transform a graph geometrically. The graph of y equals f of x is shown in figure 1.78, so there it is. Determine the graph of the composite function, y equals 2, so I start thinking, okay, that's going to be a vertical stretch, factor of 2. F of x plus 1, it's connected to the x, that's going to go 1 to the left, and then a minus 3, that needs to go 3 down, by showing the effect of a sequence of transformations on the graph of y equals f of x. All right, so here's what we need to do. We've got that vertical stretch factor of 2. Now, my vertical coordinates at -2 and 4, those are zeros. So if I multiply those by 2, they're not going anywhere. But my vertical component for this middle point is going to be at 0, 2. So my vertical component of 2 needs to be multiplied by 2, and that's going to take it up here. And now I'm going to use dashed or dotted, because this is not my final answer. And in math, whenever we have helpers along the way, whether or not it's a line or a curve, we make those dashed or dotted. Now, that was the first transformation that took place as I read this from left to right. So far I'm right here. The next thing that I have to do is shift this, translate this 1 unit to the left. So all of my points are going to move visually 1 to the left. And finally, the entire graph needs to be moved down by 3. So I will go ahead and make that happen by taking, again, these are the significant points that we're looking at. And when I say significant points, these were the points that we could kind of consider vertices in geometry. So that's the points that we want to use. Those are the ones. Now 1, 2, 3, and 1, 2, 3 down. And this is my final. So that's the one that I make solid. And just to be certain, I take a quick peek at it and I think, okay, yep, it's vertically stretched by a factor of 2. It has been moved 1 to the left and 3 down, and that's exactly what we needed to happen. Now, in this, like I said, the order matters. It is very easy for us to just go from left to right. You do need to know that with this particular graph, we could have interchanged those first 2 steps. Now, like I said, I'm trying to make sure that I take care of all of that in the homework, but I just absolutely want to get it through to you that you shouldn't be telling professors that they're wrong when you get to college if they use a different method. We actually took quite some time to decide on this as a department about how we were going to teach this to you, because there are so many right ways to teach it. So if we just go left to right, everybody will be fine. To summarize, when sketching a new graph by a sequence of successive transformations, multiplication can be done before addition and subtraction. The inside changes are the opposite of what they immediately appear to be. So keep in mind that X is the little brat of the process. It always does the opposite of what we think it should be doing. And then those outside changes are exactly what we would expect. So x is the trouble causer. And if you just think opposites of x, you're going to be just fine. So we've got a bunch of u tries here to go through, and some of these are going to be pretty basic, but some of them get pretty involved. So for each equation, determine the parent function, that's huge, and the transformations. Sketch a graph without using a calculator. Find a few key points, such as, put 0 in and see what you get. And then state the domain and range using interval notation. So we've got pieces here that we want to make sure we don't forget. And the first thing that I see when I look at A is, hey, that's a line. So normally if we were going to graph this, we would subtract 2x from both sides, which we're still going to do. And we would divide by 5. But now what we have to do is follow the steps here and talk about what was the original, the parent function, and then how was this changed. So with this one, y equals x would be the parent, because that's the parent function for lines. The first thing I see as I move from left to right that's not a y or an x is a negative sign, and that was a reflection over the x-axis. Then I see the 2/5, and I realize, well, if that's in front of x, then that's a vertical compression. Vertical compression factor of 2/5. And finally, I have the +3 in the back, so then I'm going to put then translated 3 units up. And there we have it. That's the determine the parent function and the transformations. Sketch a graph without using a calculator. Well, y equals x is our parent function. We should really put that on there so that we can make sure that all the things that we said were going to happen with the transformations are actually happening. So there's y equals x. And now this graph started at 3. And we go down 2 and right 5. And we could actually use that slope backwards so that I have something to aim at. Now, we're not suddenly going to change the way that we graph lines so that we can show each of those transformations. Lines are too basic for that. So what we're going to do instead is just realize, okay, what would happen here if I reflected that over the x-axis? Oh, yep, slope-wise, that makes sense. And vertically compressed it, so squished it down, and then translated it 3 units up. Yep, that's where I would end up, right there. And then domain and range. And this one did not have a function name because we're just talking about a line here, and we typically just use y equals mx plus b for those. So our domain here is going to be all real numbers. This is going left and right forever. So negative infinity to infinity, because at the pre-calculus level we always use interval notation if it's possible at all. And then our range, it is going up and down forever. So that will also be negative infinity to infinity. So for each of these, those are the steps that we want to go through. All right, so now the next one is y equals the quantity x plus 3 squared minus 1. So the first thing I do is identify that my parent would be y equals x squared. And typically our parents are going to be one of the 12 basic functions. So there's the squaring function. And then I think about the transformations that are going to take place. And there's my x, so that's going to be the opposite of what I see. That will be translated 3 units to the left and 1 unit down. All right. So now the next step that they had for us was sketch a graph without using a calculator. So I need to think of my parent function that goes through 0, 0, 1, 1, 2, 4, 3, 9, and has symmetry on the other side. But I'm just going to leave this as dots, with a little arrow there, because that's my parent function. And that's not my final. So my final comes from following that order of transformations that I had, which was translating 3 to the left and 1 down. So with this, all I really have to do is move my vertex 3 to the left and 1 down. And then move each one of my points 3 to the left and 1 down. away we go. And there it is. So some of these are going to be much easier to do than others, and usually it's the ones that we've had a lot of experience with, and we've definitely had a lot of experience with the squaring function. So now we have domain and range left, and this one's going to take a little more thinking. Again, they named this one y. They didn't name it an actual function name. And my domain, my arrows are showing this is going to go right and left forever. However, we are definitely not using all of the y's. There are an infinite number of y's down here that this graph never gets to. So our graph is going to start at -1, and that's included, so that's square brackets, and it's going to go up forever. So -1 to infinity. All right, next up. We have f of x equals negative, and then we have x squared plus 2x plus 3. And I realized, well, this isn't in my AH and K format, and that's how I'm supposed to look for transformations, is with AH and K, because it's the easiest thing to do. So what I would want to do with this one is complete the square to make this quadratic look like a vertex form. So I'm going to make that f of x equal to y. Going to divide everything by a -1, because when we complete the square, we cannot have anything but a 1 in front of that first term. And then I'm going to move over the 3 because it's not helpful where it is. That is not a perfect square. So -y plus 3 equals x squared minus 2x. And then we'll go ahead and do our b over 2. And my b value here is -2. So -2 divided by 2 is -1, and I square that and I get 1. So -y plus 4 equals x minus 1, the quantity squared. Now we're getting much closer to that AH and K formula. Subtract a 4 from both sides and divide everything by a -1, realizing that there are two terms here. One of the terms is the quantity x minus 1 squared, and the other is -4. So both of those have to be divided. Now, we might as well go ahead and put its name back on there. It was f of x. But now it's going to be much easier for us to talk about those transformations. All right, so first thing we need to do is identify the parent, and then work left to right on this. So we've got the parent function is a quadratic again, y equals x squared, the squaring function. And then we will reflect over the x-axis, translate 1 unit to the right, remembering that the x's are always opposite, and 4 units up. All right, now back to the fact that our parent function was a quadratic. So 0, 0, 1, 1, 2, 4, 3, 9, and then symmetry, equal but opposite on the other side. So there's our parent. But the first thing we have to do here is we have to reflect it over the x-axis. So that's going to bring all of these equal but opposite, so down to 1, -1, 2, -4, 3, -9, and then with symmetry, equal but opposite. And then we need to slide this. We need to translate it 1 unit to the right and 4 units up. So take your vertex and each of those points and move them 1 unit to the right and 4 units up. And that would be solid. Domain and range. Our arrows are showing we're going right and left forever, so that's going to be -infinity to infinity. But our range, well, we're using all of these y's, but once we get up here, 4 is the last one. So that's going to be up to 4. So those are going to be the ones that, you know, we feel like we've experienced these a lot. We've done a lot of these. These feel really good. I know what I'm doing here. And then we get to some of them that maybe we're not so comfortable with. But we need to remember using all of those transformations that we've talked about. So in D, the first thing I see is, ooh, something squared plus something squared equals something squared. Hey, that's a circle. And this one would have a center at 0, -5. And the radius would be a 2. So there it is. Now, how do we talk about that in terms of transformations? Well, our parent function is a circle. So there's the parent function for circles, x squared plus y squared equals r squared. But we don't really say specific transformation pieces about this because circles, their identifying features have to do with where's the center and where's the radius. So for these, we would say it has a center at 0, -5, and radius of 2. And again, we wouldn't just draw, you know, x squared plus y squared equals r squared because r, we wouldn't know what that is. So with circles, we're not necessarily going to have a dotted or dashed model and then a final model. We would just go to a final model with circles. So this is going to go down to 0, -5 for its center. And then we're going out 2 in every direction. Since r squared was 4, take the square root and you get 2. And then try your best to draw something that looks circular-like in there. Circles can be hard, especially as they get larger, to make something that actually looks like a circle. And then the domain and the range. And this one did not have a function name to it, so that means we'll just do D and R. And we can actually see, hey, we're using these x's from here to here, which is -2 to 2. And for the range, we are using from here to here. So from -3 to -7. And we have to reverse that because it has to be in terms of the number line there. So that's a circle. Circles aren't so bad. Now, your comfort level probably goes down a little bit when you get to the square root functions. And that's because you haven't had a ton of experience with them. But we do know that this should be turned around because it's supposed to be x minus h under there. And then I realize, oh, there's a negative in front of the x. That means I have to reflect this over the y-axis. I better see what that's going to look like. So I'm going to factor out that negative so that I can talk about this in the terms of a, h, and k with a little bit extra going on in this function. So my parent is y equals the square root of x. And I talk about all the transformations, including the negative in front and the negative in front of the x. So this will reflect over the x-axis. We will have a vertical stretch, factor of 3. We will have a reflect over the y-axis, and we will have a translation, so translated 2 units to the right. All right, so square root function 0, 0, 1, 1, 4, 2, 9, 3, just taking the square root. So there's the original. And now I want to follow all my transformations here. So I want to reflect over the x-axis and bring it down here. Then I have to vertically stretch by a factor of 3. So that means all of my y values have to be multiplied by 3. This is at 1, so now it's going to be -1, -2, -3. It'll be right down there. And then I had a -2, that'll be down at -6. And I had a -3 that will be down at -9. So now I am here. So I'm going to put a couple of dashes in there to keep the focus on that one. So we took care of reflect over the x-axis. We did the vertical stretch, factor of 3. Now we need to reflect over the y-axis. So that means all the x's become negative. And now we're here. And finally, this one needs to be translated 2 units to the right. So all of my points, including the 0, 0, going 2 units to the right. That is our final graph. And we want to make sure that it still looks like it has a curve to it. I know it had a vertical stretch factor of 3, which really does stretch it out quite a lot, but we have to be careful about that. And then we had our domain and range, and this one was named f of x way back up there. And we have to be careful with this as well. I mean, we need to look at this and figure out that our new starting point for this graph is the ordered pair 2, 0. So our x's are off to the left, and then we get to 2 and we have to stop. So that'll be negative infinity, and 2 is included. And then our y values are below the x-axis, so there's our negative infinity, and they're going all the way up to 0. And including the 0. So 0 would get our nice little square bracket there. All right, so hopefully you're feeling a little bit better about the square root function. It just takes some getting used to, and like I said, you need a little more practice with it. And I know we have had more practice in the homework as you've gone through it, so hopefully you're feeling a little bit better about that. Now, g of x. Negative 6 times the quantity x plus 5 squared minus 2. Oh, that's a quadratic again. We like those. So maybe pause the video at this point. I've given you a pretty big chunk about transformations today. Pause the video and give this one a try to see how you're doing on your own. All right, I'm looking at this one and noticing it's already in that A, H, and K format. So my parent is y equals x squared. I'm going to have to reflect over the x-axis. Then vertically stretch, huge vertical stretch here. Vertically stretch by a factor of 6. Translate 5 units to the left and 2 units down. And we'll have this. Okay, so what does that look like? Well, we have our 0, 0, 1, 1, 2, 4, 3, 9. Symmetry on the other side. You should be starting to memorize these. You know, it's one of the things the brain is marvelous with. The more we see something, the more we remember it. And then we have to reflect it over the x-axis, so that's going to bring it down. There we go. So all of our y's have become negative. And then we have this gigantic vertical stretch. And that was going to be our 6, a factor of 6. Whew, okay. So 0, 0 isn't going anywhere. If I multiply that by 6, 0 isn't going to change. But my y coordinates here are negative 1 and negative 1. So those are going to become negative 6 and negative 6. And I can't even get another transformation on here with that vertical stretch of 6 because these were at negative 4. And that would be negative 24. So almost straight up and down at this point. So I am going to define that a little bit better with some dashes, dots, so that I can make sure that we can see it. And then our skinny little upside down U shape, our parabola, has to be shifted 5 units to the left and 2 units down. So there's my new vertex. Let me switch colors. And here are my 2 points that I had that I can do my translations for. So my 5 to the left and 2 down. And there is our upside down skinny little parabola back at -5, -2 for the vertex. And that's going to be important when we talk about the domain and range. So this one was not called f. Scrolling back up, that was g of x. So we want to use our notation for domain of g and range of g. And it's a parabola, -infinity to infinity. We can put any x's we want in there. But definitely we have a cutoff for our y's again. And that y cutoff is coming up from underneath. We have -infinity all the way to -2 and including -2. So hopefully, you know, like I said, I'm sure you did well on this one because it's a parabola and you've seen lots of parabolas in your mathematical career. Now, look at that one. This is something we're probably not real comfortable with. Not only is it square root, but it has a lot of things going on here that don't seem to be in the right place. So the first thing we would do is we'd start moving them in the right place. So instead of putting the +5 in the front, let's put it in the back. And while we're writing that, we realize, well, that 4 can't be there. That's going to mess everything up. So let's factor out a square root of 4, remembering that we absolutely can do that. So if we take the square root of 4 out of there, 4x divided by 4 is x, and 2 divided by 4 would be 1/2. And then we know what the square root of 4 is. It's 2. So this is going to be h of x equals -6 square roots of x plus 1/2 plus 5. And now that looks a lot more like a square root function that we're used to dealing with, and our square root function of y equals a square roots of x minus h plus k. So move this down so I have a little bit more room to write my transformations. We have a parent of the square root function, and we have to reflect over the x-axis, and that's this little negative in the front here, vertically stretch by a factor of 6, then translate a 1/2 a unit to the left and 5 units up. And there it is. All right. So this one's going to take quite a bit of movements, so make sure you keep track of your dots. I've been trying to use a lot of color up here to show the shifting that we have to do. So normal square root, 0, 0, 1, 1, 4, 2, 9, 3. Those are our perfect squares, and of course that'll work out nicely when you're talking about square root. So we have to reflect that over the x-axis, so all of our y's become negative. Just keep track of which one is the latest one you were working on. And then we have to vertically stretch by a factor of 6. And just like we experienced in the last one, we're not going to be able to put all of these points on there. But here we're at -1, and that's going to go down to -6. So I'm here and here, and then just so I have something to aim at, I'm going to take this -2 and go down here about where -12 would be, so that I don't lose track of the fact that, yes, it is still a curve. There's not a lot of curve to it with a vertical stretch of 6 within that -10 to 10 window, but there's a curve there, and I want to make sure that I use that all the way through. Now, we've done the reflection. We did the vertical stretch by a factor of 6. Now it has to move 1/2 a unit to the left and 5 units up. So 1/2 a unit to the left, 1, 2, 3, 4, 5. There's where my new 0, 0 is going to be located at. 1/2 a unit to the left, 1, 2, 3, 4, 5. And 1/2 a unit to the left, and 1, 2, 3, 4, 5. That's why it's a good thing that I put that -12 down there, so I have something to aim at. So now, again, make sure that it looks like there's a curve going on. There's supposed to be a curve there. And we have all of our transformations taken care of. What's left is a recognition that this was at -1/2 and 5, so that we can talk about domain and range, and this was called h of x. So domain of h and range of h. So our domain we're going to be starting at -1/2 and going on to the right forever. So that'll be -1/2 to infinity. And then for our range, we're using everything down here in the basement, so that's our -infinity up to 5, including 5. So normally in class, we wouldn't be able to get through all of these, and we'd tack a little bit of this into 1-7, which deals with word problems. But because we're taking a test on Thursday, I wanted to make sure that I could get through everything that we had as far as transformations go. And we have met all of our objectives. Determine the type of transformation based on a graph or equation, vertical and horizontal translations, and reflections across the x-axis and y-axis, vertical and horizontal stretches and compressions. So that was a huge new piece. Graph a combined transformation based on a parent function. Well, that's the big whoppers that we just did here. And write an equation for a combined transformation. We actually started with that today. So we have definitely hit all of our objectives, and there is the day 2 assignment. And we probably want to have graph paper at some point, so whether or not you grab it here in class or you print it out of that black file holder in Schoology, I think that'll make things go a little faster. You don't have to use graph paper. You can always use your notebook paper if you wish to.